This is Knowledge Engineering with Semantic Web Technologies. And today we are talking about the last part of lecture number 2, RDF-based knowledge representation. And in this last part of the lecture, we want to talk about SPARQL subqueries and SPARQL property paths. Okay, so let's have again a look at a SPARQL query example. What we want to do here is we want to select all authors, and we want to select by whom these authors have been influenced. And of course, we want to have all the notable works of these influencers. So how should we do that? So one possibility to solve that is with a new construct with a so-called subquery. And a subquery is nothing else but a query within a query. It means you do a query, and based on the result of that query, you have new variables or values of variables, and they will be used in another query. So this is somehow, these are subsequent queries within a query's nested queries in that example. So a subquery usually is in the where clause of a query that is surrounding the subquery. So what do we do here? Just look at the example. So we look first at the outer query. What we want to have or what we want to select in the end are, of course, the name of authors, the name of their influencers, and the names of their notable works. So first of all, within the where clause, we want to select authors and the influencers of authors. And we do this, for example, by posing another select statement within the where clause of the surrounding statement. And this new inner subquery has to be embraced again by curly braces to separate this from the rest of the where clause. So within these curly braces, a new select starts, and here we want to select now authors and influencers, and we do this simply, look at the where clause of the inner select, by stating authors are of type DBO writer, and of course they should be DBO influenced by their influencer. So this is the inner part, the inner subquery. The result of that will be authors and influencers. And now I join the result of this subquery with the where clause of the outer query, which here goes on like, I'm looking for what are the notable works of the influencers. So I'm looking for a triple which consists of influencer, DBO notable work, and work. And then they will be combined simply with the influencers which come from the result of the inner query that you see here. So in the end, you will get a list with authors, influencers, and the notable work of the influencers. And you can try out this query if you want to, again, following this link in the right corner here. So you will end up in the dbpedia endpoint as usually. And you see here, we have here the inner query of the subselect, and we have the outer query, and we run the query, and you see here a huge list of authors, their influencers, and notable work of the influencer. So for example, we have here the author Edgar Rice Burroughs. You know, for example, he has written Tarzan, and one of his influencers was Arthur Conan Doyle, and of course the notable works of Arthur Conan Doyle, you might know that, are here all the Sherlock Holmes novels, so for example. And you can see this here for many other authors too. So this is quite easy. This was a so-called subquery. So within a subquery, first you create a result, and this result is then joined with the result of the outer query. Usually, and this is really important, with subqueries you can embed queries within a query. And of course, you should always look at the order, the subquery, so the inner query is computed first, and then the outer query is computed. So this sometimes has effect on, of course, the complexity of the query and then also on the runtime of the query. But feel free to experiment a little bit, because this is not the only way to express a SPARQL query which delivers exactly this result. So this is only one of many possible ways. Okay, these are so-called subqueries. So subqueries also are available in usually SQL or SQL for relational databases. So you might already know that. So what is new and different from relational databases are in SPARQL's so-called property paths. So what are property paths? So property paths are a new mean to define ways through a SPARQL graph. So usually a property graph is a possible route through an RDF graph between two given graph nodes. So already your plain simple triple that you look at is a property path. But here, the route is only of length 1. It means it's one property that you have to cross. If you have to cross a path of several properties, then you end up in a property path which is longer than 1. But there are many possibilities to combine these properties to a property path. So the most trivial case, of course, is the plain RDF triple pattern that we already know. This is a property path of length 1. So this is not different from what we already know. If the path is longer than 1, so then the first possibility that you have is you could define, for example, alternatives. So this means the result should match one or both possibilities of a given alternative pattern. This might look like the following. So here, for example, I define a property path which consists of two properties which are combined via this vertical line between the properties. I'm looking for books and their titles. And the title of the book could either be expressed by a triple book, DC title, and then the title, or it could also be expressed by book, RDFS label, and then the title. So this is an alternative graph expression, and you can of course use this graph expression within the where pattern, so as a graph pattern in your SPARQL query. Alternatives are expressed with this simple vertical line. Okay, this is one possibility, the so-called alternatives. More interesting are the so-called sequences. So sequences are one property after the other that have to be crossed. And of course, then the sequence should be longer than 1, because otherwise you will end up in a trivial triple pattern that you know already. So just look at the following example. What do we have here? So we are looking for a variable x, which, and this obviously is a FOV profile, which has assigned a FOV mailbox, a FOV mbox, that has a specific URI, which is given here as a constant. So this should be then mail to Alice at example, for example. So this is not a valid mail address, but it's only working for an example. But what we want to have here is, this is specified in the second graph pattern that you see here. This is specified here. I want to follow a property path. This X should know somebody, and these people who are known by X should also know somebody, and then we want from these that are a path of length 2 away, we want to have the names of them. So we want to know who knows the people of n, X. And we want to have the names of them. And this property path simply is expressed by combining the properties simply with a slash, as you see here. And this property path can be of arbitrary length. So what is done here by the SPARQL processor, the graph, the RDF graph, is simply filtered for a property path that consists of these three distinct properties in this given property path. So this is quite interesting, but of course you could express this also with the already available means in SPARQL. You could say X knows Y, Y knows Z, and Z has the name. So this would be then three different triple patterns which form a basic graph pattern. So this is nothing else than what is called syntactic sugar here if you look at the property path of an arbitrary length. But it can get more complicated. So let's have a further example. What you could do, for example, you could simply reverse the use of a property in a triple pattern. So we are reversing the direction of the triple, which means if you're looking to our example, X has the mailbox and then the URI of the mailbox. This is the same like I could reverse the triple. I could first as a subject write the mailbox, and then I write the property, but in front of the property I'm writing this little character which is called a hat or a caret, and this little character means I should interpret the triple in the reverse order, which means I should treat the subject as the object and the object as the subject. So here I reverse this. you might ask, so for what use is this? So what's the intended use? Of course, for a single property path which is only of length 1, this usually does not make sense because you can easily revert it. But it's interesting if you use it, for example, in combination with a property sequence, because then you will end up in so-called inverse path sequences. So just have a look at that example here. What are we looking at? We are looking at a graph pattern. So we are looking at X, again in a FOV profile, and we are looking for persons which are known by X. And then we combine this sequence with, again, FOV knows, but then in the reverse direction. So what does it mean? So first, of course, we are looking for somebody who is known by X. And then we are looking for people who also know the same previously unknown node that is known by X. So we want to know people who are known by X and are also known by other people. And of course, we want to know who are these people. And definitely we should apply a filter expression which here states X should be something different than Y, because, yeah, sure, every node that is known by X is known by X. So therefore, the Y variables I'm looking for should be different from our starting point, and therefore I apply this filter expression. So this would be a combination of a direct path and an indirect or inverse path, and they are combined within a sequence. So I'm looking, so you see this, or you can easily represent this in a graph, and in the graph it's much more obvious than only in the plain SPARQL statement what is really meant by that kind of expression. So inverse path sequences are really interesting, but again, you could definitely also express this with your already available means. The next thing that I'm going to show you is not so easily expressible, and this is really something completely new, because you can also define sequences of arbitrary length. So you do not specify the entire sequence, but like in a regular expression, you could say, okay, this part of the sequence should occur at least once, but as many times as it is available here. So you do not state an end, so not length 3, length 4, length 5. It's an arbitrary length. Everything which is here in the example which uses the FOV knows property more than once. And for this, to indicate that, you do this in the same way like for regular expressions. This means after the URI of the property, you are using one of the regular expression identifiers, either a plus, which means this property should occur at least once, or you use a star or a multiplication sign, which indicates this property might occur at least 0 times or as many times as possible. And then you can combine this again to another sequence expression. And this is interesting, especially, for example, for class hierarchies. If you want to compare properties according to their class hierarchy, or if you want to compare classes according to their class hierarchy, and you have no idea how deep in the given class hierarchy you are, you simply use something like, for example, here, this regular expression, so a property path of arbitrary length. So we will try this then, of course, in the exercises for the lecture. So let's look at our example here. Again, we are looking for somebody that is known by Alice here, the owner of our mailbox. So Alice is our X in that example. And of course, we are looking at the name of this one who is known by Alice. But the path, as we see here, must at least be at length 1. So this, again, y1 will be definitely, and the name1 will definitely be in our result, but the path can also be longer. So we are also looking at people who are known by the one who is known by Alice. So we are looking for who knows y1, then we end up in y2 and the name of y2. And again, the path has not ended. Now we can also look for somebody who knows or who is known by y2, and then we end up here in y3 and the name of y3, and so on and so on. So this follows a path of arbitrary length until there is no path to follow. So you should use, of course, expressions like this with care, because if you make a mistake or by chance you could cross or traverse the entire graph that is available. And this, again, might be too complex for the SPARQL endpoint you are currently using. So use this expression with care, but of course it can be useful, as you see here. Okay, so we had inverse path sequences and path sequences of arbitrary length. The last thing, what you also can do, you can of course negate entire property paths. So let's have a look at the example here. What do we have here? We have two, in this triple pattern, we have a subject and an object, y and x. And they should be combined via a property path which is given here, and the property path is negated, which means, so in the property path we have RDF type or the inverse relation of RDF type, so either x is of type y or y is of type x, and we negate that path, which means we are looking for triples which are related in a triple with y by anything but the RDF type expression, or vice versa. So, and this can be excluded simply by using here the exclamation mark in front of the path expression. Then you are looking at the negated property path. This might also be quite useful for some occasions. Okay, so to close this section of the lecture, let's take a look at an interesting example. We try to apply these property paths here. So the example is, who are the authors who were influenced by the influences of Jules Verne? So what we are trying to look for is, so we have given a specified URL, which is Jules Verne, and we want to look at by whom has Jules Verne been influenced and who else has been influenced by these influencers. And this can be simply expressed by a property path, as you see here in the where clause of our SPARQL expression. So first we have, of course, the fixed value Jules Verne, and then comes the property path. And there I first look at the people who have influenced, so who Jules Verne was influenced by. So the first one is DBO influenced by. And then I combine this with the same property, but in the other direction. So I want to look who else has been influenced by these people. And then, of course, I use here influenced by influences as the variable that I select. And of course, like in the case before, we know, of course, Jules Verne was influenced by the same people as Jules Verne, so we don't want to have him among our results. So therefore, I simply constrain this by a filter expression where I say the influenced by influences variable should, of course, not be Jules Verne himself. So let's try this out on our SPARQL endpoint. Here I have again the same expression at the official DBpedia SPARQL endpoint, and I run the query, and you will end up by a table which is again called influenced by influences, and you see a list of authors who have been influenced by the same people like Jules Verne. And here you will find, for example, Virginia Woolf, Ambrose Bierce, Harry James, Robert Louis Stevenson, and many other authors. So this was an example how to play around a little bit with SPARQL property paths. So feel free to use the official DBpedia SPARQL endpoint to apply all what we have learned right here. SPARQL is a very powerful query language. So this usually ends the official section of Lecture 2. If you are interested in more details about SPARQL and about RDF databases, which are the basis on SPARQL, you might follow the extra part of this course, but of course here the official part of the course ends. And we will continue then later on with the third part of the lecture, where we will talk about knowledge representation and ontologies.